Right, so we're given a lot of information about this cuboid and asked to find eventually the vectors OM and I think it's MN on the question. But before we do that, let's take the information we know and actually put it on the diagram. So OA is 2 units. So from O to A is 2I. But let's just put 2 because it's 2 units, which means all the other lines which are parallel on all other edges of the cube are going to be 2 as well. And we know that OC is 4. And so OC is J. That means that line as a vector would be 4J. And of course, the top is the same. And this top is the same. And when we get down to AB, it's 4. But we're told that AN is equal to 3NB, which means it's in the ratio of 1:3. In other words, this is a ratio 1:3, which is very handy because it's 4. And you can break 4 up into the ratio 1:3 by having the lengths 1 and 3. M is the midpoint of DF, and we're going to try and work with that and find the 2 vectors. Okay, to make our life easier, let's get a copy of the picture. So to find the vector OM, we can use any combination of vectors that we know that starts at O and gets to M. So what I would do, I would go from O to A, which is 2I, and then from A to D, which is, oh, we haven't put that one on, and then go from D to M. Okay, we were told OG is 2 units, and so of course DA is also 2 units. Right, so what that tells me is OM is equal to, I'll write it out, OA plus AD plus DM. All right, and we really know those things. OA is fairly easy. OA is 2I, and so we'll have 2I. And it's a vector, so put a squiggly line under it. AD is 2K, so we write 2K, little squiggly line, indicate it's a vector. DM is slightly trickier. DM is half of the diagonal, but the diagonal is made up of DE plus EF. And so that means we're going to do a half of DE is 4J and EF, it's going away from the positive direction of I and it's 2. So it's going to be negative 2I. It's negative 2 is going in the negative direction of I. And that is our vector OM. Right, so OM, let's put the like terms together. We have 2I minus 1I. All right, we'll take all the steps. 2I plus 2K plus a half of 4 is 2, 2J minus a half of 2 is 1, just 1I. And that means that OM is equal to 2I minus 1I is just a single I. Let's put the J second, plus 2J, and then plus 2K. So that's OM in terms of I, J, and K. For MN, hopefully we remember, if you want to find the vector from one point to another point, it equals the position vector of N minus the position vector of M. The position vector of N is fairly easy. We can start at O because it's just ON. And we can go to A again, and then we can go from A to N. If we add those 2 vectors together, we have the position vector for N, and we already know what N is. So for N, we're going to have 2I plus 3J, and then we're going to subtract M, which is OM, from the origin to M, which is I plus 2J. And don't forget to put it in brackets, so we're subtracting every part of the vector. So what we have is the minus sign gets distributed to everything. We have 2I minus I, which just turns into 1I. We have 3J minus 2J, which becomes 1J, and we have negative 2K. Right, and we have our two vectors, OM and MN, in terms of I, J, and K. For the vector equation of a line through MN, we need two parts. We need a point on the line and we need a vector in the line. Well, we have a vector in the line. MN is the vector in the line. And we also have a point on the line because M is a point on the line, N is also a point on the line. So either of those will do. And so for the vector equation, we can just say the vector R is equal to the point M. All right, we better write it. OM plus some variable multiplied by MN. We know those two. So the vector equation, which means the vector R, is equal to OM, which is I plus 2J plus 2K plus any real number multiplied by Mn, which is I plus J minus 2K. And that will get us to every vector which is on the line. All right, on to part C. Part C, show that the length of the perpendicular from O to the line through Mn is something. Grab our line. What the vector R is the vector from O to every single point on the line. So one of those vectors is going to be perpendicular to the direction of the line, which is the direction vector in the line. So what that means is, if they're perpendicular, the scalar product is 0. So we're going to take one of the vectors, we don't know which one yet, we're going to do the scalar product with the direction vector, which is I plus J minus 2K, and that's going to equal 0. If we can solve that, we're done. So we're going to take the R vector and turn it into just a single I, J, and K. In other words, we will get I plus Ti is 1 plus T times I. And then we're going to add 2J plus TJ, so it's going to be 2 plus TJ. And then we've got 2K minus 2TK, so it's going to be plus 2 minus 2TK. And we're going to do the scalar product with I plus J minus 2K, and that equals 0. All right, to do the scalar product, we multiply x by x, y by y, and z by z. Or in other words, what's in front of the I is the x, what's in front of the j is the y, and what's in front of the k is the z. So we're going to get 1 plus t multiplied by 1 plus 2 plus t multiplied by 1 plus 2 minus 2t multiplied by negative 2 equals 0. That should be solvable for t because t is the only variable there. Let's expand every bracket and see what we get. We get 1 plus t plus 2 plus t plus, not plus, let's go minus 4 plus 4t equals 0. Leave the t on this side and we'll get 4t plus 1t plus 1t is 6t. Take everything over to the other side. Oh, what do we have? We've got negative 4 plus 2, sorry, plus 2 plus 1 is negative 1. We take it over, we get positive 1 is equal to 1, and so t is equal to 1 on 6, which then tells us the point, it actually tells us the vector r, which is also the point at where it is perpendicular. So the vector r is, we're going to put t into the r vector. You can put it into the line version of r, or we could put it into the compressed version. It doesn't matter. It doesn't matter. They're exactly the same thing. So let's use the compressed version. We're going to get the vector O to m, which we'll just call r at the moment, is equal to 1 plus t. T is 1 on 6. So 1 plus 1 on 6 is 7 on 6. 7 on 6i. And we've got 2 plus 1 on 6, 2 plus t. 2 plus 1 on 6 is 12 on 6 plus 1 on 6, 13 on 6j. And we've got 2 minus 2 times t. So we've got 2 minus 2 times 1 on 6 is 1/3. So we've got 2 minus 1/3, which is 6 on 3 minus 1 on 3, which becomes 5 on 3k. So this is the vector which goes from the origin to the line, and it is perpendicular to the line. We just have to find the length of this vector, and we're done. So the modulus of the vector is equal to the square root of every part squared. So we've got 7 on 6 squared plus 13 on 6 squared plus 5 on 3 squared. And surprise, surprise, we put those fractions into a calculator and we end up with 53 on 6, which is what we had to show was the distance. We could write that if we want, therefore, it's not a vector, is it? Let's just say line mn is the square root of 53 over 6.